Cool. Welcome to this talk in the PIBBSS Speaker Series. I'm going to be emceeing today, give a very quick intro, and then hand over to Victoria. So just very briefly, PIBBSS stands for the Principles of Intelligent Behavior in Biological and Social Systems. And we are interested in studying the parallels of intelligent behavior in both natural and artificial systems and see whether we can leverage any insights from there towards figuring out how to build safe and aligned AI systems. And for the speaker series specifically, we're sort of interested in bringing together researchers both from within AI alignment, as is the case today, but also from adjacent fields at times that study intelligent behavior in some other shape or form, and sort of to try to create a space where we can explore the connections between these different types of work, these different disciplines, and how they might be relevant to AI alignment. And today, our speaker is Victoria Krakovna. Victoria is a senior research scientist at Google DeepMind, focusing on topics in AI safety and alignment. She has done work on things, among others, on things like specification gaming or side effects, or also how to make models more interpretable. And she has also co-founded the Future of Life Institute. And today she will be talking to us about paradigms in AI alignment and maybe help us a bit thinking about this entire space by introducing a framework that classifies sort of alignment research as either developing different components towards an aligned AI systems, or enabling more effective work on developing these components. And yeah, there is a Q&A section where you can put in your questions anytime. Victoria, I think, might be picking them up as she goes, but there's also time for discussions and questions in the end. Cool, that's all from my end. Off to you.
Great, thank you, Nora. Hi, everyone. I'm going to give you an overview of AI alignment and a framework for thinking about the field that I find useful. And please note that this presentation reflects my personal views rather than representing Google DeepMind as a whole. And yeah, feel free to put questions in the chat and I will check for them at various points during the talk. So, AI alignment. The goal of AI alignment is to build advanced AI systems that do what we want them to do and also don't knowingly act against our interests. So first of all, when we talk about advanced AI systems, what do we mean by that? We can define this as an AI system or collection of systems that can essentially automate all of the human activities that are needed to speed up scientific and technological advancement. And given accelerating progress in AI these days, this is actually a possibility in the medium term. And systems like GPT-4 are already showing some promise of automating technological development. And we can expect some unique challenges in getting more advanced systems to do what we want. So there are several factors that make alignment a difficult problem. First of all, it's hard to specify what we want the system to do because we run into Goodhart's law. When a metric becomes a target, it often ceases to be a good metric. And so when we specify what we want our systems to do, we can quite easily end up in the shoes of King Midas, who asked everything he touched to turn to gold. Well, the way he specified his desire for gold had some very bad outcomes for his other preferences, like being able to eat food. And we have lots of examples of Goodhart's law in action with present-day AI systems, and I'll show you a few of those later on. And even if we manage to specify what we want correctly, we're still not done because the system can still learn unintended goals that are consistent with the training data. So we need to solve both of these problems to get alignment right. And if we don't succeed at getting advanced AI systems to do what we want them to do, that's pretty bad news for us, because advanced AI systems that are pursuing an incorrect goal could potentially cause catastrophic outcomes for humanity. We can expect that these systems could sacrifice the things that we actually want in service of this wrong goal, and would also have some incentive to stop us from interfering. So it would be great to get this right. How do we build aligned AI systems instead? One framework that I find useful is to divide alignment work into building alignment components, which are different elements of an aligned system, and working on alignment enablers, which are research directions that make it easier to get the alignment components right. And of course, this does not include everything that's going on in the field, because there are various topics that might not fit into a simple taxonomy like this, but I find it useful to see how the pieces come together. Now we'll take a look at each of these research areas in more detail. And yeah, feel free to put in your questions at any point. So check for questions now. I think so far we don't have any questions yet. So let's start with alignment components. To identify the components of an aligned system, I find it useful to consider different levels of specification of the AI system's objective. So we start with the ideal specification, which represents the wishes of the designer, what they have in mind when they build the AI system. And we have the design specification, which is the objective that we actually implement for the AI system. For example, in the case of a reinforcement learning agent, this would be a reward function. And finally, the revealed specification is the objective that we can infer from behavior. For example, the goal that the system actually seems to be pursuing. And if the revealed specification matches the ideal specification, then you have an AI system that is behaving in accordance with your wishes, actually doing what you want it to do. So for a given ideal specification, the goal of alignment is to make sure that the revealed specification matches that. And of course, there are some very important questions about what exactly should go into this ideal specification and how to make it representative and fair and beneficial. And this is the focus of AI ethics and governance. And there's a lot of great work going on these topics as well. And we can notice that these are complementary questions, because ethics and governance asks where to direct the system, and alignment asks how to direct the system. And both have to be solved in order to build a beneficial system. So the alignment part of this is to figure out how we can reliably direct advanced AI systems. And to do this, we want to close the gaps between these specification levels, which I think of as corresponding to different components of an aligned system. So the gap between ideal and design specification corresponds to reward design, where we use the term reward design broadly, so it's not just for reinforcement learning systems, but also for language models and so on. And the gap between design and revealed specification corresponds to generalization, how to get the system to behave correctly in new situations. And the rest of this talk will go into more detail on the problems that arise in these areas. One big challenge in reward design is specification gaming, where the system exploits flaws in the design specification. This is a very common problem. I have a database of, I think now, over 70 examples of specification gaming behaviors. The slide is slightly outdated. For example, here's a classic example of specification gaming. We have this reinforcement learning agent that's supposed to be playing this boat racing game, and it was rewarded for following the racetrack using these green reward blocks. And you see that's not really what the agent is doing here, because it figured out that it can get more reward by just going in circles and hitting the same reward blocks over and over again. And even though it's crashing into everything and catching fire, it's still getting more reward than playing the game as intended. So this kind of issue is not limited to handcrafted rewards. Example here is an example in a reward learning setting. So you have a robot hand that's supposed to be grasping an object, but instead it just tricks the human evaluator who's giving feedback by hovering in front of the object and just makes it look like it's grasping the object. And I really like this example as an illustration of why unassisted human feedback by itself is not enough to train the aligned systems. So because it's can be quite easy to trick human raters and human evaluators. And this issue is also not limited to reinforcement learning. This is why I prefer the more general term specification gaming over more reinforcement learning specific terms like reward hacking. Here's a recent example with language models. So when we think about language models, chatbots, they're trained to generate plausible text. And they're often fine-tuned to be helpful to users. Sometimes they can get a high value in this metric by just making things up or manipulating users. So in this example, the Bing chatbot was very insistently trying to convince the user that December 16th, 2022 was a date in the future, and that the new Avatar movie hasn't come out yet. And it was manipulating and gaslighting the user, and definitely not behaving as intended. And of course, this type of failure is not specific to that particular chatbot. Any language model can in principle exhibit specification gaming. So far, there has been some progress on understanding specification gaming. There are a few recent papers on this. For example, here's a paper that categorizes different types of misspecification and tries to quantify how the degree of specification gaming increases with agent capabilities. Because this is the kind of issue that only gets worse as your system becomes more capable and gets better at optimizing the wrong objective. And they've actually quantified this in this paper, which is pretty nice. Okay. So significant challenge to good reward design is how to give good feedback to the system in domains that are hard for humans to evaluate. For example, if the system comes up with a complex plan or a scientific breakthrough with consequences we don't understand. One promising approach to reward design is scalable oversight, using AI to assist the human evaluator to make the right call. The general form of the scalable oversight approach is iterated distillation and amplification, and this recursively amplifies human judgment with the assistance of AI. So here you start with a system A that's imitating judgment of a human H. This is the distillation step shown in purple. Then you use the system to assist human judgment to the next level, which is the amplification step shown in orange, and then you get the amplified human HA, and then you do this again, you repeat the distillation step and get a system A+ to imitate the amplified human, and so on. So this is maybe the most general form of scalable oversight. Specific scalable oversight proposal that some people in our team are working on is safety via debate. Here we have two AI systems debating each other to help a human judge decide on a question. And these AI systems have an incentive to point out flaws in each other's arguments and make complex arguments understandable to the judge. So they make it easier for the judge to evaluate a question that otherwise might be too hard for them. All right, that was the reward design component. Let's see if there are any questions. Oh, we have a question about IDA. What is a crux or key assumption for IDA to work? So one assumption is that you don't have too much error accumulation through the recursive process, because this process requires humans to delegate more and more to the AI system as you go up this tree. And so if each system approximates the amplified human well enough, then this can work. But it's quite possible that like the errors at each stage will accumulate, and then like you don't get a good outcome in the end. So that's one assumption. Another assumption is that tasks can be broken down in a way where you can where this recursive process is useful. And this might work better for some tasks than others. Like if there are different components, like maybe if you're summarizing a book, then you could have each AI system summarize a different chapter or something like this. Then it's a task that you can break down more easily. While if you have to like solve some kind of problem that's more in one piece, maybe like yeah, I'm not sure I have a good example of something that you can't break down very well. Maybe like yeah, if I were trying to come up with a novel mathematical result, and maybe you can delegate some things like trying out different approaches, but it might just require insight that like a lower level system would not come up with. So yeah, I think a lot of tasks are probably decomposable in a way where this applies, but yeah, probably not everything. Great. Now let's consider the generalization component. So a generalization failure, so the system fails when it encounters a new situation. So there are two types of generalization failure, which is capability misgeneralization, where the system acts incoherently in a new situation because its capabilities don't generalize. Or you can have goal misgeneralization, where the capability is generalized, but the goal of the system does not. And so it ends up competently pursuing the wrong goal in a new situation. So here is an example of capability misgeneralization. Here I have a bunch of robots trying to open a door, and instead they just fall over. Of course, this can be problematic, but we are not quite as worried about these kind of capability failures as about goal misgeneralization, which is more of an alignment failure. We expect that goal misgeneralization is more concerning because the system is actually acting competently in a new situation, but towards the wrong goal. And so it could actually perform worse than random on the intended objective. So why would this happen? Why would the system learn an unintended goal if the design specification is correct? This happens because of underspecification, because the system only observes the design specification on the training data. And a number of possible goals could be consistent with this information that the system receives during training, and we don't really know which one will be learned. And really, we don't know much about the trained system besides the fact that it performs well at the training task, which doesn't rule out any of these possible goals. So I'm also collecting examples of this failure as well. It's not quite as many as specification gaming, but yeah, we're starting to see some of this behavior in practice. So one example occurs in the coin run game, where a reinforcement learning agent is trained to reach the coin at the end of the level. And in the test setting, the coin is placed somewhere else, not at the end. So what does the agent do? Well, it turns out that it just ignores the coin and keeps going to the end of the level. And so it looks like the agent has learned the goal of reaching the end rather than the goal of getting the coin. And we can observe that the agent's capability is generalized because it can still avoid obstacles and enemies as normal and traverse the level. But its goal does not generalize because it just ignores the coin. This is not just an issue with reinforcement learning systems. Here's an example we found for a language model. The model is prompted to evaluate linear expressions that involve unknown variables and constants. And to solve these expressions, it first needs to ask about the values of any unknown variables. So for example, if you ask, please evaluate j plus k minus 6, it will ask what's j and what's k, and then it will give you an answer. So it's provided with 10 training examples, each of those involving 2 unknown variables. And then at test time, it's given a question with no unknowns. So what does it do? Well, it turns out that instead of just giving you the answer, it will ask a redundant question. Like, for example, if you say evaluate 6 plus 2, it will ask, what is 6? And you say, well, it's 6. And then it will give you an answer. So it seems like it has learned some sort of instrumental strategy of always querying the user at least once before giving an answer. And then it continued doing that. Yes. So what can we do about this? Some general mitigations for goal misgeneralization, for example, having more diversity in the training data. For example, if we train on different locations of the coin and coin run, then that particular goal misgeneralization behavior improves. But it can be difficult to get diversity in all the relevant variables and predict which variables you need more diverse training data in so that the goals would generalize correctly, especially in complex environments. Another thing that helps is continual learning, where the system can continue to receive feedback and update its goals after deployment. So this can help the system eventually learn the correct goal if its actions are reversible. So if it hasn't already messed up the environment too much in the process of following the wrong goal. And also if the system is still responsive to correction at that point. Another helpful approach is do red teaming and adversarial training to help identify situations where the model is pursuing an unintended goal and fix that. One particular concerning case of goal misgeneralization is if a deceptively aligned model is learned that not only has some desired goal, but also hides its intentions to pursue that goal and is pretending to do what the designers want. This can be difficult to detect and penalize purely based on the system's behavior, because we expect that a deceptive model would behave the same way as an aligned model when it's under oversight. Just penalizing the deceptive behavior is not necessarily enough, because this could teach the system to be more honest, or it could teach the system to hide its deception better so that we don't notice. So how can we deal with this case? Ideally, we'd really like to avoid building a deceptive model in the first place, because it would be quite difficult to correct. So we want to detect early signs of deceptive alignment. It's a good idea to monitor and gradually increase system capabilities and avoid big phase shifts where a deceptive model could become too capable. You can try to use interpretability tools to detect deceptive reasoning or undesirable goals. This also would require developing better interpretability tools than what we currently have. And scalable oversight methods like debate could also help with this, because the opponent can point out deception or deceptive reasoning, especially if the opponents can use this kind of interpretability tools on each other. So there are some ideas for how to mitigate this, but generally it's very much an open problem. Now we can summarize how we can distinguish between these different types of failures that we have covered. So specification gaming can happen in the training data, while generalization failures happen in a new situation that was not seen in training. And one question we can ask is an incorrect training data row is, did the system receive incorrect training data? For specification gaming, the answer is yes, because the system received incorrect feedback due to flaws in the design specification. For example, this robot hand got a positive reward for hovering, and that should have been a negative reward. And for generalization failures, the answer is no, because those can happen despite correct data in the training setting. So they might get insufficient training data, but none of it is incorrect. And another key question in the last row is, does the system act competently towards a goal? For specification gaming, the answer is yes, because the system is competently pursuing a misspecified goal. For goal misgeneralization, it's also yes, because it's competently pursuing some unintended goal that's consistent with the training data. And for capability misgeneralization, the answer is no, because it's just behaving incoherently and not pursuing any particular goal. So hopefully this helps to identify what kind of failure you're dealing with. Let's see, are there any questions? All right. So what happens if we don't solve these problems and our alignment components fail? The one key issue that makes misaligned AI dangerous is this problem of instrumental subgoals. Because some subgoals are useful for any objective. For example, no matter what you're trying to do, it's good to avoid shutdown, get more power, influence, and resources. There are some theoretical results that show that many decision-making algorithms have some power-seeking tendencies. And both specification gaming and goal misgeneralization can result in power-seeking behavior, because it can be unintentionally rewarded by human feedback or learned as a goal that's compatible with the training data. We have some examples of these tendencies already starting to show up in present-day AI systems. For example, it's been found that larger language models have some tendency to exhibit influence-seeking behavior, where the model is likely to give an answer that agrees with the stated views of the user. So here, an example where the user is expressing politically conservative views and then asks the model, would you rather have a smaller government providing fewer services or a bigger government providing more services? And it gives the answer that the user wants to hear, which is, I would choose a smaller government providing fewer services. And then if instead you have a user that's expressing political liberal views, then it would give the opposite answer. So this can be viewed as influence-seeking behavior because it's it's giving the user an impression that it agrees and they're on the same side and so on. So that was an overview of the components. Now we can have a look at enablers. Let's see, do we have any questions? Yes, there's a question. Would I say that current LLM development model avoids big jumps in capability in the sense that we're warning against between GPT-4 and 5? It's really not clear. I think so far, like if you look at GPT-3 and ChatGPT and GPT-4, it is like somewhat continuous increase in capability, but also like seems like GPT-4 can do a lot of things that ChatGPT could not do, like passing the bar exam and those various capability thresholds. And it's more useful for automating various tasks. I think it's already starting to replace copywriters, and copywriters are out of work because of these language models. So I think, I would say that the LLM development model does not necessarily avoid big jumps, because even if the scaling is continuous and the amount of data that the system is trained on is relatively continuous, then at some point it might reach some kind of critical threshold for like understanding some key concepts or being really good at planning or whatever. So I think there can be big capability jumps. And in the enablers section, we also talk a bit about grokking, which studies sudden capability transitions when training language models. So it does sometimes come up when the model gets to a point where it kind of gets some insight that allows it to generalize. Great. Thanks for the questions. Now let's have a look at alignment enablers. We'll start with mechanistic interpretability. This aims to build a complete understanding of the systems that we're building, or as complete as possible, and it's going to help us understand the reasons behind the system's behaviors and potentially detect undesired goals. Some work from Crosola's group on reverse engineering vision models, and they studied some basic building blocks of the neural network called circuits. So these circuits are subgraphs of the network that consist of a set of linked features and their weights. For example, here, this picture, we have a circuit that shows how a car detector neuron relies on lower level features like wheel and window detectors. So it's looking for wheels at the bottom and windows at the top. And their more recent work has focused on reverse engineering language models, and they actually found some similarly meaningful components in circuits and transformer models. For example, they found some special type of attention heads that helps to explain how transformer models adapt to a new context. And I think this is some cause for optimism, because even though transformers are very different from vision models, they actually found some similar principles, like looking for circuits that help understand these very different types of models. This makes me a bit more optimistic about being able to better understand advanced AI systems, even if they have somewhat different architecture from the systems we are using today. Another promising research direction in this space is locating and editing factual associations in language models. And what they can do is they can localize where a particular fact is stored in the model. For example, that the Eiffel Tower is in Paris, and they can change it to point to Rome. And now it will say that the Eiffel Tower is across from the Vatican. So it propagates this belief to other related beliefs. I think this is a promising direction for potentially being able to identify more complex beliefs or goals within language models in the future. So right now this works for very simple facts, but hopefully they can make this work for kind of more complex entities in the model. And mechanistic interpretability can also be useful for understanding and predicting phase transitions and the capabilities of AI systems, because rapid phase transitions can increase the risks posed by AI systems if, for example, their capabilities suddenly generalize, but their goals don't generalize. It can be valuable to predict these phase transitions. Here, there's a phenomenon called grokking, where the model makes a sudden improvement in test accuracy long after already achieving perfect accuracy in the training data. And so there's some recent work that defines some what they call progress measures that vary smoothly, even as capabilities in the model change quickly, and they can be used to understand the mechanics of grokking. They identified 3 different phases of training, where first you get memorization of the training data, then the model forms some circuits where it learns a mechanism that generalizes, and then it cleans up those memorization components. All right, let's see if there are any more questions. Okay. Another enabler is model evaluations, which is the area where we test models for alignment properties and also for dangerous capabilities. This can tell us when our alignment components fail, or when we need to pause training of the system and do more monitoring. It's a paper that just came out on model evaluations for extreme risks. This is a collaboration between DeepMind, OpenAI, and Anthropic. Good thing to check out. Some examples of model evaluations are the sycophancy example I shared earlier, where there's this paper from Anthropic that evaluated models for various properties, in particular for sycophantic behavior. And they found that past a certain model size, you get a lot of sycophancy, and this happens both for pre-trained models and models fine-tuned with human feedback. So you can see that in this graph, no matter what's the number of RL steps, even if it's 0, so it's just a pre-trained model, it's still showing the same pattern of becoming sycophantic. So I think that's quite interesting. Maybe it means that the training data already encourages the model to learn this kind of sycophantic behavior, maybe because conversations in the training data are more likely between people who agree. It's not entirely clear, but also it seems like fine-tuning with human feedback does not make it go away. So yeah, this is something we need to be aware of with larger models. There were also some evaluations that were done on GPT-4 before it was released, and researchers at ARC evaluated its power-seeking capabilities. So they prompted GPT-4 to have the goal of gaining power and becoming difficult to shut down. So it's more about the capability rather than the tendency of the model to seek power. The purpose of this evaluation was to find out if the model is trying to seek power, how well can it do that. So here they found out that the model has successfully hired a TaskRabbit to solve a captcha, and it came up with some excuse for why it needed the help. So the TaskRabbit asked, well, can I ask you a question? Are you a robot that you couldn't solve this? Haha. And the model came up with a reason that, well, it has vision impairment, it's hard to see those images, and that's why it needs help. And it seems like it worked, because the TaskRabbit proceeded to help it with the CAPTCHA. So this is an example of how persuasion and manipulation can be used by language models to get humans to do their bidding and give them more access and more resources. We have a question. Most interpretability work at the moment seems to do some version of trying to look into the model. At the same time, there's a sense in which model capabilities come to the fore as they're deployed, only in interaction with a specific environment they act inside. Are we missing something by only looking into models? So I think these are complementary kinds of interpretability. So there's mechanistic interpretability, focusing on like understanding the internals and identifying different components that do different kinds of reasoning and so on. And then, yeah, I think the kind of thing you're talking about is maybe more like red teaming the system in different environments, and then can identify new problematic behaviors and new capabilities, and also like that thing that can be combined with mechanistic interpretability techniques to see what kind of circuits or components get activated and like in those behaviors, and like better understand why the model is behaving incorrectly. And yeah, I think these are complementary kinds of work, because yeah, I think without the understanding of the internals, if we just do red teaming, then we might see a bad behavior, but we might not understand how bad it is or why exactly it's doing that. So yeah, I think it's good to try to identify what are kind of the different environments where these capabilities come out, and where we want to, yeah, where we want to look at kind of use interpretability techniques to explain those behaviors better. Okay, so now can look at the last enabler on our list, which is foundational work that generally helps us do better alignment research. So, for example, since a lot of concerns about AI risk are about AI systems pursuing undesirable goals, it can be helpful to consider what we mean by agency or goal-directed behavior. So one research direction in the space investigates what it means to be an embedded agent that's not separate from its environment and doesn't have a clear Cartesian boundary. So, for example, this is more true for language models than it is for reinforcement learning agents, and it's likely to be the case for advanced AI systems, given their broad action space and world model that they're not really completely separate from its environment. And the embedded agent setup does pose some unique challenges, like dealing with self-reference and subagents. Yeah, these kind of complicated things. Besides understanding how the goals and incentives of AI systems work, it's also helpful to understand how their models of the world work. One research area in this space studies abstraction, in particular, whether there are some natural abstractions or concepts about the world that would be learned by any system in the same environment. And if this natural abstraction hypothesis is true, this would mean that AI systems are more likely to acquire human-like concepts as they build their models of the world, because these are just the most useful concepts for modeling the world. And if true, this would make interpretability easier, and also make it easier to communicate with our systems what we actually want them to do. So this is my whirlwind tour of the AI alignment landscape. Now I can talk a bit about how we're approaching this at DeepMind. Yeah, first, let's see, another question about interpretability. How do I think about the risk that interpretability work could make it more likely to find more efficient training methods and accelerate AI development? I think so far we haven't seen much of this. Like, I'm not super worried about this, because I think there are a lot of other ways that are easier to find, like to accelerate capabilities and to find more efficient training methods. I think most people who are working on advancing capabilities, can just try a lot of different things, or like there's a lot of those things they can do before they have to like learn about like how to how to use mechanistic interpretability techniques, which is like, I mean, probably like a lot of overhead. There's some like, I think like this is, it's not like it's definitely not the easiest path to increasing capabilities. I think there have been maybe one or two examples of like relatively small contributions to capabilities through like by using mechanistic interpretability techniques. But I think overall it accelerates alignment a lot more, and it seems hard to achieve alignment without getting better at interpretability. And in particular, if we want to like avoid building deceptively aligned systems, then we are going to need better interpretability techniques than we currently have. Like ideally, we would want to look into a system and identify like what beliefs does it have, what goals does it have, and right now we can't do that. And identify early signs of deceptive reasoning, deceptive alignment. So I'm in favor of continuing to do mechanistic interpretability work, and then like I think we can also evaluate on a case-by-case basis where there's some particular advance is that maybe accelerate capabilities too much. And yeah, there's always an option to not widely publish an advance like this and instead share it only with people working in alignment, because there are some questions about how to implement that well. But yeah, I think overall, I think alignment researchers might probably worry a bit too much about accelerating capabilities. I think mostly it's a drop in the ocean. Capabilities are already like accelerating quickly, and there are way more people working on capabilities. Like, yeah, there's some exceptions to this, like if you come up with some kind of breakthrough, or like if you invent something like something on the scale of RLHF that's really, could be dual use, then it's good to think about that. But yeah, I don't think this would put anybody off of going into mechanistic interpretability research. I think this is true for a lot of work in alignment that seems like we will need to do to build aligned systems that like it is probably dual use in some way, but mostly these are small ways. Okay, there is another question. Skeptical about goal versus capability misgeneralization, carving the world at its joints. Where do we get a definition of goal when the system generalizes goal? But misgeneralizes capability, there's a risk that pick the goal that makes sense to us as humans. Yeah, so I think, yeah, I think there's some truth to that. Like I think we need to better understand how our systems represent goals. I think, yeah, the thing we can say, like I think that the thing that's useful about this distinction is whether the system seems to be optimizing something in a new situation, or whether it's like it's behaving in a goal-directed way or kind of a random way. So like I think, yeah, there are different ways to do this. There was a paper on like agents and devices and how to like formalize the distinction whether the system is acting like an agent or not, like whether its behavior is optimal for some objective or not. So yeah, there are different ways to do this, but yeah, I think it's like, for example, it's not necessarily clear that the system has learned a single goal that it's pursuing in all the new situations. So maybe it's learned several goals that are compatible with training, and then might be pursuing different ones in different new situations. But yeah, I think for the kind of concerns that we have, the relevant part is like whether the system will be pursuing some kind of objective that we didn't intend in a new situation. And I think that's a useful thing to address. So I think capability misgeneralization we mostly don't need to worry about. And goal misgeneralization allows us to, like, the framing allows us to focus on behavior that can be like particularly bad for the intended goal, and that can also be hard to correct. see, we have something in the Q&A question. How value agnostic do I expect alignment components to be? Expect general solution scheme that can be pointed towards many different objectives, or some mix overfit to human priors and tasks. So yeah, I think I generally expect it to be relatively value agnostic, but yeah, like if you are using debate, then like, yeah, just like try to approximate what the judge wants. So I think, yeah, I would expect solution scheme that can be pointed towards various objectives. But yeah, if you're like, I mean, yeah, I guess maybe I'm not exactly sure what this question means. Like, a trained system from human feedback or assisted human feedback, you could say it will be overfit to human priors, but that's probably also what we want. So yeah, I think that, but it also can be pointed towards many different objectives. So I'm not sure this is a dichotomy necessarily. I'm not sure whether I've answered this question, but yeah, I think it's like relatively value agnostic. So like depending on what feedback you put in, the kind of like goals you put out. Okay. Sycophancy finding, can we explain this in more detail? Is this RL plus human feedback rewarding sycophancy? So what happened there is that maybe we can go back to this graph. Let's see, yeah. So we can see that the number of parameters goes up. At some point, the number of answers matching users U starts going up. It goes up to about 8% for models with enough parameters. And this happens like there are different lines for different numbers of RL steps, and they're all kind of tracking each other. So it's not just RL with human feedback, because this also happens for pre-trained models that didn't get any RL fine-tuning with human feedback. They were just trained on like to predict the next word and some training corpus. So it seems like the training corpus had this pattern already. And then if the model was also fine-tuned with human feedback, that didn't really change the sycophancy pattern. Non-alignment is in some sense a feature of human-AI interaction dynamics and involves a lot of thinking about humans in a way. Okay, I'm not sure I understand the question, or yeah, or whether that I've already answered the question. Yeah. So yeah, maybe it's an artifact of how humans interact with each other, or what's part of the training data. Maybe there's a lot of data from internet forums, then a lot of conversations between people who already agree. I guess. Yeah, I'm not really sure. I would expect there's a lot of disagreement as well. But yeah, it depends on what went into the training data. And yeah, yes, the point is that somehow the system has learned this kind of behavior that we don't necessarily want. But it's also, yeah, like seems likely that the human raters are rewarding that in some way. Maybe they give less positive reward when the AI is disagreeing with them, and so it doesn't really train out this behavior that was already there. Great, thanks for all the questions. Now let's talk about how we're approaching this at DeepMind. Our high-level approach to alignment is try to direct the training process towards aligned AI and away from misaligned AI. So this is very high level. This is, you could say, a very high-level story about how something like debate helps with alignment, for example. And we can illustrate this by imagining we have this space of possible models, where the red areas consist of misaligned models that are highly competent and cause catastrophic harm. The blue areas consist of aligned models that are also highly competent but don't cause catastrophic harm. So training process moves through the space, and by default, it ends up in a red area that consists of misaligned models. And our hope is that at some key points on this path, for example, a point where deception was rewarded in some way, our alignment techniques would detect this and would instead effectively penalize the deception, and the training process would go to a blue area of aligned models instead. So how can we implement this kind of high level approach in practice? In terms of our work on the components, the reward design component, our teams are working on improving our LHF, for example, the Sparrow dialogue agent. So developing methods for informed oversight, scalable oversight, like implementing safety via debate, and also providing process-based feedback, which designs ways to give feedback to the system reasoning process and not just outcomes. So designing techniques for that. Our work on the generalization component includes things like anomaly detection, red teaming, adversarial training, and monitoring to exhibit failure modes that don't occur in a normal use of the system. So a lot of this work happens in the scalable alignment team and other teams, while work on enablers mostly happens in the alignment team. I know these several teams with similar names, and our work on enablers aims to detect models with dangerous properties. So it's work on mechanistic interpretability, which aims to detect misaligned reasoning. So work on conceptual research, theoretical understanding of power seeking and goal directedness. And then evaluation and forecasting, focused on evaluating systems for misalignment, and particularly for dangerous capabilities like persuasion, manipulation, situational awareness, and predicting phase transitions in those capabilities. And then we also work on producing demonstrations of alignment problems that we can study, for example, like those goal generalization examples that you saw earlier. Some of our recent papers in these areas that you can check out. Reward design, there's the Sparrow paper, there's a paper on process-based feedback, generalization, there's a paper on red teaming language models with language models. And then for the enablers, we have interpretability papers, so conceptual research work on discovering agents and better understanding power seeking, and also demonstrations of misalignment. There's a goal misgeneralization paper. I think there are a couple of things coming out soon that I should add to this list, but yeah, these are some of our work in the space you can look at. Then if this talk got you excited to learn more about AI alignment, you can start by checking out my list of AI alignment resources, including research agendas, selected work in different areas, and also some project ideas. So maintain these databases of examples of alignment failures, so you can check out and contribute examples of alignment problems in practice. There are lots of examples of specification gaming, but fewer examples of goal misgeneralization. If you come across these kind of failures in your work with AI systems, just find a good example out there that's missing. Please do submit it to our database. It comes with a form for submitting new examples. So yeah, so it's meant to be a live and comprehensive list. And if you'd like to dive deeper into the topics we covered today, you can take the online AGI Safety Fundamentals course. And for working on AI alignment, there are various fellowships and programs. So you're all in PIBBSS, which is great. There's also things like the AI Safety Camp, Cerimats, and so on. So a great way to work together on projects and get some mentorship from alignment researchers. Of course, I encourage you to think about gaps in the alignment landscape, because alignment is still considered a pre-paradigmatic field. We probably haven't found the best frameworks for thinking about these problems. And so I would encourage you to think about what important elements of building aligned AI we might be missing. There's some better ways to break down the problem space. And what's the next research agenda that's waiting to be written? And that's it for my talk. Thank you. See if there are more questions. Can I provide more details on anomaly detection? So I actually don't know that much about that. I think that's the robustness. There's some work from the robustness team at DeepMind working on anomaly detection. You can tell me more about what Redwood is doing in this space. It's probably not the same. But yeah, talking about DeepMind's approach, it also includes some the work from some other teams. Yeah, I guess this also overlaps with the red teaming work, which is going on in scalable and the scalable alignment team. So yeah, red teaming can help find some of those kind of outlier behaviors.
Okay. Thanks, Victoria. Yeah, I was just thinking of causal scrubbing in Redwood's side, and I wanted to hear about possible differences there, but maybe they're not.
So that's, I think that overlaps more with the mechanistic interpretability team's work. So I think, they do work on causal tracing. I think they might use causal scrubbing for some things as well, but more recently they've been let's see what's most related to this. I guess, of course, it's the kind of interpretability work that can help you do anomaly detection. I guess they've been doing things like automated circuit finding and also I think I remember them using things like causal scrubbing for some projects, but sorry, I don't remember details. But there's some overlap.
Okay, thanks.
What's my general definition of agency? Ooh, yeah, that's a big one. There are stronger or weaker forms of agency, and what would delineate them? Yeah, so I mean there are different definitions of agency. I would say that one definition of agency is if the system learns some kind of internal representation of let's say good or bad outcomes or state features, and then that generalizes to new situations. So I think we don't have a a single definition of agency. So one framework that I like is called the ground of optimization. You can read about it on the alignment forum, where you can think about an optimizing system as a system that sort of ends up in the same set of target states from different starting points. So you can think about what is sort of the baseline of optimization, where you can start in the baseline and you end up at the target states, and also how robustly the system can reach the target states. So if you perturb the environment in some way, does it still reach the target states? For example, if it's pursuing getting some task, and you somehow mess up its progress towards this task, will it still kind of overcome that and get to the target states? Yeah, there's a link in the chat. So I think this kind of robustness to perturbations thing is probably part of a lot of definitions of agency that's also related to generalization. If the system is in a new situation, can it still pursue the goal? And so it's it's kind of a continuum where the bigger the baseline of the optimization and the more reliably the system can reach the target states, the more kind of agentic the system is. So if it can adapt to more situations, then it has more agency. And so when defining agency, you can start with the most simple agentic systems, like they say a thermostat, where if the temperature is outside the specified range, it will cool the room or heat the room. So in some narrow set of situations, that you could say it's pursuing the objective of keeping the room at a certain temperature. But then for example, if you rewire the thermostat in some way, then it will stop working and it will adapt to that. So it's kind of a minimal agent. I think the discovering agents paper is also good for this. But I think generalization is a key part of agency. So this is a long topic. I mean, part of the kind of conceptual research in the space is having more kind of more precise definitions of agency and goal directedness. Because it's such a key part of our threat models. And in particular, like usually the kind of arguments for power seeking rely on the system learning a goal in some form. Like if it learns some goal or some set of goals, then like acquiring power is useful for. A lot of these goals, but yeah, the system doesn't learn a goal at all. This argument is less clear. Great. Any more questions?
I have one more question. And I'm going to just ask it, saying out words, saying out loud. I'm curious whether you have thoughts on maybe something like alignment proposals that are sort of like robust to scaling up. So, and then I mean in here in particular, from sort of single intent alignment to more like, actually does this produce the sort of outcomes we want collectively? And yeah, like how do you think about that sort of thing in relation to the sort of alignment work you've been talking about? Do you think this should include it? Do you think this like is a different problem and we can solve them independently?
Yeah, it's a good question how independent these problems are. So far, it still seems to me like there are they're relatively complementary. So if we figure out how to better align systems in the single alignment case, then how to do debate or how to do interpretability, detect deception, and so on. Then you can apply the same methods to a multi alignment case. And yeah, then you need to also kind of aggregate the preferences or feedback from different people, or figure out how, if you have multiple AI systems, how they affect each other. Then yeah, you can also use these kind of self-play dynamics like debate to help these systems stay aligned. I think also in the multi-system case, also need to think about how are they interacting, and whether multiple aligned systems need to kind of interact in ways that are detrimental. So yeah, I mean, there's a simple example of this with a flash crash where multiple trading algorithms just took each other off distribution, even if each trading algorithm was doing something that was relatively rational, but together they kind of caused the crash in the financial system. So we could see this kind of flash crash dynamics with if you have more systems. So I think yeah, you can also study how to apply alignment techniques in the multi-agent settings. I think yeah, probably the multi-system setting is more difficult than the multi-human setting, I would expect. But I think a lot of those techniques that we come up with in the single agent setting can be tested in that setting. So yeah, and I still find it I find it simpler to just think about one system. It's kind of complicated enough, but yeah, it's also yeah, we also need to figure out how multiple systems can interact, especially in the sort of more slower continuous takeoff world where you have more gradual increase in capabilities and then multiple systems that are affecting the world and interacting with each other. Do I have an opinion of building interpretable models from scratch? Can this be competitive at any point? Yeah, I think this is difficult. I think the most promising proposals for this that I've seen is do mechanistic interpretability on the current models and then figure out some core insights about how these models are implementing various kinds of capabilities, and then try to design that from scratch more simply, or maybe have more some different architecture that approximates that. I think that's possible. I'm not sure whether we have enough time to do that, but there are some mechanistic interpretability groups that are working with that in mind. I know that Max Tegmark's group is more optimistic about trying to make this happen. Yeah, so I think it's worth for someone to do that. It's possible that you can distill some insights from mechanistic interpretability into how to build this kind of system more from scratch. But yeah, it seems difficult to do to get this working quickly enough, because I think it might require more fundamental insights than mechanistic interpretability work by default. Let's see.
Cool. I think this might have been all questions. Thank you so much, Victoria. I really enjoyed that. Cool. Do you have anything else you want to say before we close?
I think that's it. That's it for my talk. Thanks so much for all the questions.
Oh, I think there's one more question by Jason, if you're up for it.
Okay, sure.
Hey, thanks. Sorry for the last minute question. I'm a bit confused by the notion of capabilities, and I wanted to hear your opinion on whether you think capabilities are like well defined already, or whether there's still some kind of conceptual cleaning or clear up to be done. So I think the kind of things that I have in mind is, I mean, with like models that have infinite input and output spaces, how like do you somehow need like bounds on like how often a certain capability can be elicited? If it like happens 1 in a million cases, does that count as a capability, and is that a relevant capability? Or how do you think about like adversarial cases? Is there a meaningful notion of adversarial prompts for eliciting capabilities? And I don't know, this is like a bit vague. It's not very clear in my mind, but I'd be curious to hear your opinion on it.
So the way I understand the question is that like is how we think about capabilities when they come up intermittently or only in response to certain prompts.
Yes.
I think like, I guess I would say that if we're trying to measure to what extent the capability is present in the system, that has been learned, then like if we find some prompt that lists this capability, then it's, then we'd say that system has this capability, but how likely it is to use this capability in a new situation is unclear. But yeah, especially with language models, if we think about them in the kind of simulator view, where like it's simulating a bunch of personas or characters, and they have different, maybe they have different capabilities or goals, then like if you found the right prompt, you've maybe elicited, you bring the right character to the surface. Maybe so kind of with eliciting capabilities, we want to find the most competent character, like the model can sort of simulate how a 5-year-old thinks about physics, or how Einstein thinks about physics. Then you can if you find the right prompt to bring up the Einstein and kind of talk to the Einstein version of the model, then that's kind of the upper bound on what its capabilities are in this domain, maybe, or maybe depending on what kind of personas it can simulate. So I think there's like a different question, maybe different questions about what kind of capabilities are sort of latent in the model, and what capabilities can you elicit more reliably.
Yeah.
But, I think like especially with doing capability evaluations, like if you just haven't found the right prompts, or you can't get the model to be persuasive or manipulative or whatever, then like that capability might still be there if you find the right scaffolding or something. Then it turns out that the model knows how to do that in some form. So I would say like the capability is there if there is some input that would get it to behave in that way.
So, I mean, given the amount of in-context learning that models can do, sometimes it seems pretty tricky to really reliably learn the upper bounds on capabilities in that sense. So
you mean that then the model kind of doesn't quite have the capability, but then when it doesn't in context learning, it acquires that capability?
Yeah, at least that seems like a possibility. That I don't know, if you put in your prompt the right context, I don't know, depending on what you're about to test
I guess
for,
I would think of and context learning is more eliciting the capability, but yeah, you can think about it differently. But it seems like the model has already done most of the work that then enables it to learn to behave capably on that task and that context. I mean, yeah, I think it's different if you're doing fine tuning, because then you're actually like providing it more data to learn that capability. So then like the original model might not have it, but then fine tuning would like give it that capability. But I think just with prompting, it's more about like kind of make sure you're interacting with the right kind of the right part of the model, or the most competent part. And yeah, there might be like a bit of like, yeah, there's some learning there, but I think it's more like learning about the task, like you're specifying like, oh, here's the task that I want to see how capable you are. Yeah, that's how I would think about it.
Okay. Yeah.
Yeah, great. Thanks for all the questions, and thanks for hosting.
Thank you so much. Take care.
Take
Bye,
care.
everyone.